So we all know about what submodular functions are, and as Satoru mentioned, till now we have been maximizing. So now we are interested in finding a set which has the minimum value, and obviously monotone set functions are not of any use. So we are going to assume that f is non-monotone, and unlike previous talks of maximization where the problem was NP hard, one of the amazing things about submodular functions is that this unconstrained submodular function minimization, so find the set A which minimizes fa, is actually solvable in polynomial time. Okay. So the history in a line is something like this. In the 70s, Jack Edmonds proved the theorem which puts it basically in NP intersection co-NP. I'll cover it later. 81 it was put in P, so it was solvable at polynomial time using the ellipsoid algorithm. 85 Cunningham gave the first combinatorial algorithm, but it ran in pseudopolynomial time, which means that the running time depended on the function value. So if the function value of any set is at most f, it ran poly in f. Polynomial would mean poly in log of f. But in 2001 there was this breakthrough paper, and two of the authors are present here, which gave the first combinatorial polynomial time algorithm. And the current best is this O tilde n to the 5 by Orden in 2006. So this slide is maybe 8 months old, so I think I had to change this because a paper by Lee, Sidford and Wong, which we will hear more about on Wednesday, which actually gives, so this is, I'm lying here probably, there are some other terms which they will clarify, but it's basically n cube time algorithm, and you know, that's a very exciting development. So maybe all of my talk will become moot after their work, but hopefully not. Okay, so what I'm going to talk about is none of these algorithms, right? So what I'm going to talk about is something that predated the first, predated Cunningham's algorithm. So in 1976, there was a heuristic proposed by Philip Wolfe about a purely geometric problem. We're going to hear about it a lot. And in 84, Satoru Fujishige proved that if you can solve the geometric problem on the base polytope, again I'll be clarifying these things, together you can use that to do submodular function minimization. And this heuristic, using Wolfe's heuristic to do a geometric problem to solve submodular function minimization, is called the Fujishige Wolfe heuristic. Okay. So why care about it? Well, it seems that it outperforms empirically the provably polynomial time algorithms out there. So this is a paper by Satoru Fujishige and Isutani. So these are examples. So the function is a cut function from various graphs in some data set, and the thing to notice is that this is the performance of the Fujishige Wolfe heuristic. These are the performance of the all the known till then known polynomial time algorithms. It will be interesting to see where the current best algorithm lies in this graph, but this was the state of affairs. So in general, it seemed that Fujishige Wolfe heuristic did better. I should warn you that it's not super fast. It's not that they're solving submodular function minimization in linear time or anything, but it's still way better. And the question was how good is it in theory? And basically, we'll see that the heart of the matter lies in how good Wolfe's algorithm about the geometric problem, which I'll talk about, is. Yeah.
Could you go back?
Sure.
Do we know? Okay, that's the power of the number of vertices, and that's running time in seconds, minutes, out. You don't know.
I just wanted to show the difference in the ratios, and now I switched it off.
I'm sorry about that.
Yeah, but relative, I was disappointed. I don't know. Seconds, yeah, there's the answer, Promthi. So no non-trivial guarantees were known for this Wolfe's heuristic till our work, and what we show is something rather modest. We show that this heuristic is pseudopolynomial. So this is the precise thing. We show that in n to the 4 f square time, you can get to the exact optimum for integer value submodular functions, where f is this. So it's you can think of it as the largest singleton value. I should at this point mention that empirically it's not clear if the dependence of f is absolutely necessary. And as I'll show you, the Wolfe's algorithm is probably a candidate strongly polynomial time algorithm, but we don't know lower bounds either. So that's sort of an open problem, but this is sort of a modest thing that we could show. Okay, good. So so cast of characters. So given any function, there is this polytope called the base polytope. It has basically it's an Rn where n is the size of the universe, and it has a constraint for every set, and basically it says that the total x mass in any set is at most the set function value, except for the universe it adds up to the function value. Okay, so it's an exponential many constraints, and this is for any set system. But when the set function, any set function, but when the set function is submodular, this polytope is really beautiful. And so there are a couple of theorems that I think you should know. So one is that, both by Edmonds, that if doing linear optimization over this polytope is really fast. Okay, so you can solve it by the greedy algorithm. Most of you probably know it. Given so x is the cost vector here. So if you're given a cost vector x, you just order the elements so that they're in increasing order, and then you just increase qi as much as you can. So it's not important. It's a simple sorting algorithm that gets you. Throughout the talk, let's assume that there's an oracle which gives me the submodular function value in unit time, as in otherwise there's just this evaluation oracle time that comes in. So this can be done. So linear optimization is easy on the base polytope of a submodular function, and more importantly, how it's connected to submodular function minimization is this minimax relation. It says that for any submodular function, the minimum value, this is the thing that you're interested in, is equal to this. So this is, so x minus u is just taking the negative components of this x vector, and the positive components are brought to 0. So it's just summing up the negative components and maximize this function over all points in the base polytope. So note that this is not something like this, otherwise we would just be done. So this is not a linear function in x. On the other hand, this can be expressed as a linear program with few other constraints. I just have a new variable for this thing, and I just say that that thing is at least xi and at least 0. So in some sense, so there are two things to note. So suppose I give you, I tell you that the function value minimum is some 100. So there is a way to certify it that it's at least 100 by giving an x whose this value is 100 and proving that x is in BF. And to prove that x is in BF, I need to express it as a convex combination of n vectors of BF, and the vectors of BF just look like this. So this basically puts this function minimization in NP intersection co-NP, and in some sense, I may be wrong here, this is the only certificate we have for the value, the minimum value of submodular function. So just to prove that your function, you're done, basically it goes via exhibiting such an x. Okay. Okay, so that's Edmond's. Now comes Fujishige's theorem, which says that, okay, let's go back to the base polytope BF and let x star be the minimum norm point. It's the point which is closest to the origin. Okay, so it minimizes this value. Suppose you could find it, then submodular function is trivial because you just look at the negative entries of, so order x star like this. So x star is at 1 is at most x star 2 up to x star n. Just look at the negative x values, and that set is a minimizer. In particular, you show that this set, this salmon colored set, is actually the function value is equal to the total x value here. So that will be the certificate that this function is the minimizer. Okay, so this boils down this combinatorial problem of finding the minimum submodular function value to a geometric problem, right? I given a polytope, I want to find the minimum norm point, and moreover, I can do linear optimization over this polytope very fast. Okay, good. So, okay. So most of these continuous optimization problems don't solve the problem exactly. They find the value up to some error. So you need a slightly robust version of Fujishige's theorem. So it's saying, suppose I find a point x which satisfies this condition. So it's the norm is smaller than something plus delta. So it's basically if you solve the linear optimization problem with x as the cost vector, this norm is at most this plus delta. So why is this a surrogate for being close to minimum norm, because basically it's not too hard to see that if x satisfies this, then x is very close to the minimum norm point. And then don't bother it right now if you don't see this, but this is one surrogate. So if you have such a point x by some method, then you can get a set which is at most, so this is, remember, a lower bound on the optimum plus some more additive error 2 root n delta. Okay? So if you find so if delta were 0, which is in which case x would be x star, the minimum norm point, then I will get the optimum submodular function value with a proof that it is the optimum. Okay? And this is just a robust version which says if you come delta close, I have an extra root n delta additive. Okay? So if this cartoon basically says that the set that you find is, well, you don't cap at 0 anymore, but you go a little more and find one of these level sets. Yeah. So what does that mean? So if f were, okay, so this we proved this, but a similar bound was also proved earlier by Francis Buck, and maybe even earlier. I don't know. So but it's not a very difficult proof. But what it means is that if f is integer valued, then I can choose delta to be 1 by 4n. Okay? So, and I'll get exact submodular function minimization. So here's the goal, right? So if I can find a point x which satisfies this condition with this error 1 by 4n, so this is not really very small, it's only 1 by polynomial, 1 by linear, then I can solve integer value submodular function exactly. Okay? So in the next 15 minutes or so, I'm going to completely change gears and just describe an algorithm, Wolfe's algorithm, which is going to say how to find the minimum norm point on any polytope, not just the base polytope. So this will be a right sort of time to pause and see if there are any questions on submodular functions at all. Okay. So this is, I think, the more interesting part, because the algorithm, as I said, works well, and we just did a very cursory analysis, and I'll probably just mostly spend time on the algorithm. So here goes. So these are two definitions. So convex hull of a set of points, so we all know, so between two segments is this line, 3 points is this triangle, and the affine hull is basically the smallest translated subspace which contains the points. So 2 points is the line going through it, 3 is the plane going through it, and for single points, convex hull and the affine hull are the same. Here's the deal. Finding the nearest to origin or the minimum norm point. So we want to find the nearest minimum norm point on the convex hull of the base polytope. But given a set S, finding it on the convex hull is a hard problem. But finding on the affine hull is easy in the sense you can just, there's a closed form formula for this using, so it's very easy. Okay? So we're going to use this fact, or Wolfe's algorithm uses this fact. So it has a definition. Wolfe defines a set of points S to be a corral if the minimum norm point in the affine hull actually ends up in the convex hull. So for instance, in this case, for these 2 points, this is the origin, the minimum norm point is here, it lies in the convex hull. So these 2 points form a corral. These 2 points don't form a corral because the minimum norm point on the affine hull is actually lies here. Okay? If you have just 1 point, it's a trivial corral because the convex hull and the affine hull is the same. Okay? So that's a corral. So given a corral, I can actually find the closest point in the convex hull. So in a nutshell, Wolfe's algorithm moves from one corral to another till it finds the optimal corral, and in the process it might go via some non-corrals. How do I know that I've reached optimality? Well, X is optimal if basically this holds, right? So if I'm optimizing in this direction X over the polytope, that hyperplane should support the whole polytope. So in other words, x square, the x dot x should be at most, so x dot x should be at most x dot q for any q in the polytope. Okay, so this is reminiscent of the weird property x square being x dot q plus delta. So we will sort of terminate when I get delta close to this thing. Okay, So Wolf's algorithm maintains a state always. So S will be a set of vertices in the polytope. X will be a point in the convex hull of this set S. Initially, S is any arbitrary vertex. You could find it using linear optimization, and X is that point itself. Until I reach this condition, so till X square, so I am delta close to being optimum, I run some major cycle and a minor cycle, and I'm going to tell you what major cycles are and minor cycles are. They'll depend on this set S, X and S, and I update the state. So what's a major cycle? So it depends on whether the set S is a corral or not. So how do I check if something is a corral? I go to the minimum norm point in the affine hull. If that lies in the convex hull, I'm a corral, otherwise I'm not. So if S is a corral, so I go to the minimum norm point, I find basically the Q, so I use X as the cost vector, and I find the nearest point, I find the point which minimizes X dot Q. So in some sense, this is discovering an extra point in the origin side of X. So if you look at this hyperplane, this corral, it's discovering a new point, and the major cycle says add it to S, move on. So major cycle ends. So major cycle increments the size of S. What happens if S is not a corral? For example, in this case, I added, so from the previous slide, I added Q to S, and now this is the picture. And in 2D, the affine hull of 3 points is the whole space. So the minimum norm point is the origin itself. So it's not in the convex hull, at least in this picture. So you just move X, you connect the old X to this point Y and see where it hits the boundary. Okay, and this is my new X. So I'm moving this X up to here. Okay, and then since it's in the boundary, some points are redundant for describing X. So in this example, I don't need B anymore to describe X. I delete that from the set S, and I move on. Minor cycle terminates. So minor cycle decrements the size of S. Okay, so that's it. That's what goes on. I have X and S. Each iteration is either a major cycle or a minor cycle, and major cycles increment the size of S. Minor cycles decrement the size of S. And one thing that is not too hard to see is that in each cycle, the norm, Euclidean norm, is strictly decreasing. What that means is the set S. The corrals cannot repeat. So the number of iterations can be just bounded by the number of sets S, which is finite but quite large. So this was already there in Wolf's paper, and the question was, is there a better analysis? I would go out and say there's probably no lower bound known for this algorithm. So this is the algorithm. Okay. So what did we show? We showed us. Let me read out the statement. So for any polytope P, we can get to this error delta, X square is less than this thing, in these many iterations. So an iteration is either a major cycle or a minor cycle. D here is the diameter of the polytope. So note that, okay, D here is the diameter of the polytope, and I take 1 by delta time. Okay. So recall for submodular function minimization, sort of to go back, what did we want? We wanted a point X in BF where delta was 1 by 4n, and the diameter of the base polytope, again it's not hard to see, is at most root n times this F. F was the maximum singleton entry. This is because this is a trivial bound, because you know exactly how the vertices look. So if you put them together, and I did not say how much time is spent in each iteration. So this is already there in Wolf's paper, as someone pointed out. So we are doing either linear programming, which is just an n log n plus n calls, or we are doing affine minimizer, but we are doing many of them, so you can amortize, do it in order n square time. So each iteration takes order n square time amortized per iteration, and there are n square f square iterations. So that gives me n to the 4 f square. Okay, so that's the state of affairs of Wolf. So let me give a sort of a whiff of the proof. So this, if anyone is aware of the Frank-Wolf algorithm, they will say that they would recognize that this sort of term comes out there as well. And indeed, the proof is similar to the Frank-Wolfe algorithm, at least in the case when there are two major cycles in a row. So the algorithm is going on, there's major, minor, major, minor, but if there are two major cycles in a row, then I get a lot of, I make progress, and that's, so the following picture shows, let me just show the picture. So I had x1, I minimized, got q1, and then I went and find x2, and that also lied in the convex hull. So my norm basically dropped by x1 square minus x2 square. So this is basically Pythagoras theorem, and this is nothing but the projection of x1 onto this x1 minus q1 line, but the projection is nothing but x1 square minus x1 dot q1 divided by the length of q1 minus x1, which we are saying is the at most the diameter. So this is really, and why is this large? Well, this is large because I have not terminated yet. So whenever I make two major cycles, I make progress. So I think the only thing we sort of observed is if you make a major, minor, major cycle. So minor cycles remove our intuition completely. We don't know what goes on. But if you do one, if there's only one minor cycle, then also things are not too bad. So one minor cycle sort of looks like this. I was there, then I moved a bit here, and then again I got a major cycle. This is basically a very high level proof. It says that if so x1 went to x2, then went to x3. If x2 is already far away from x1, I have already made progress. And if not, then x1 and x2 look very similar. So I can sort of assume that I'm at the same x2, and then x2 minus x3 will be large because it's like a major, major. Here we are using the fact that if I moved a vector x1 to a vector x2 just close by, how much does the linear optimization value change? So this is some sort of sensitivity analysis of polytopes of diameter d. This is what is needed to prove here. So we can handle major, 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 minor, major, and then comes this. So yeah, if major, major, or major, minor, major, then the norm decrease happens, and then comes this sort of trivial observation that if there are t iterations, because major cycles increase and minor cycles decrease, if there are two minors, then decrease is happening, strict decrease is happening. So in t iterations, there is at least t by 2 major, major, or major, minor, major. I write this paper here because in our submitted version we had t by n. I guess we're not caring about n's at that time, but this was pointed out. So in fact, let me sort of announce a result that is not yet public yet, but is upcoming. They basically prove that for any polytope, Wolfe's algorithm gets delta close in log 1 over delta times m square. So we were d square by delta, and for submodular function minimization, maybe you save one n factor. But if you are generally interested, it gets log 1 over delta times m square. But m is not a diameter anymore; it's something called the eccentricity of the polytope. And for the base polytope, this is not clear yet. So, am I out of time, or
you have 5 minutes?
I have 5 minutes? So I also have the proof of the robust version, but okay. So before I go, maybe I'll just take home points. So what was so there's this reduction of submodular function minimization to a purely geometric problem, and I think Wolfe's algorithm for just the geometric problem is quite interesting. We just did a cursory analysis. I think whether dependence on the diameter is indeed needed or is it strongly polynomial time is interesting. In particular, given any polytope as a convex combination of vertices, can you find the minimum norm point in strongly polynomial time? So that's a question that I don't know the answer to. So another approach is, although empirically it works well, I don't think there's a huge empirical study being done. In particular, is there a dependence on f in these empirical studies? That's something. So can you empirically disprove the strongly polynomial timeness? That's another thing. And so this is the robust Fujishige, but it's pretty late. Let me just skip this because it will take more than 5 minutes. So maybe later on. So I'll just end. Thanks.